First, the hydrates of aldehydes and ketones. So as the name implies, this has to do with the equilibrium between the keto form, the aldehyde form, we call them all the keto form, the keto form that's in equilibrium in the presence of water with the hydrate. So what I want you to notice there is that we've added a molecule of water to this. So we put formaldehyde in water. This is a common reagent, formalin, used to preserve biological samples in many instances. And in the case of formaldehyde, it is 99.5% hydrate, 0.5% formaldehyde. Now, formaldehyde is the volatile component, and of course what we can smell very clearly from those formalin solutions. Now, if we look at acetone, so now we go from an aldehyde, the simplest aldehyde, to the simplest ketone. We can draw the hydrate here. And in this case now, we have 0.1% hydrate, 99.9% ketone. So there are huge differences in these. The example I always like to introduce students to is chloral hydrate. So trichloroacidaldehyde. So as we put strongly electron withdrawing groups on the carbon here, 3 chlorines, makes this partially positive. And of course our carbonyl group is partially positive also. We'll look at that in a little more detail in this chapter in a minute. So chloral hydrate exists, or chloral, in the natural environment, in an aqueous environment, exists as the hydrate. Now, chloral hydrate. Now, I'm a hard-boiled detective fiction buff. They're great reading if you've never read any. And The Maltese Falcon, the originator of the field, was made into a movie by Humphrey Bogart a long time ago. So you might have seen that movie where they use knockout drops. They put knockout drops in Humphrey Bogart's character's glass, his drink, and he takes that and he then passes out and wakes up with a terrible headache. That's chloral hydrate that are knockout drops. Now, how does this occur? This is important because it introduces us to the fundamental of the carbonyl group. It's important that you get this. We're going to look at it in this simple case. And it's important that you understand where things are reversible and where they're not reversible. So let's just take, I think what I'll do is acetone, because it makes the drawing easier. Now, the hydration can be both acid catalyzed and base catalyzed. So here first is the acid catalyzed mechanism. Now pay attention to the arrows that we're going to use. So if we have an acid, this can be protonated. It will be protonated on the lone pair. That is a reversible reaction to produce this oxonium ion And it looks like I'm sneaking up off the page there. So let me just move this slightly. Maybe my camera has moved a little on me. We make this oxonium ion, the protonated acetone. Now, if the carbonyl here is partially positive, then this carbonyl has an even greater partial positive charge because it's now been protonated. And we can see this in the resonance form that's accessible for this compound. So if we draw a resonance form, there's now the carbocation form, and we can see very readily why we have partial positive charge at the carbon. Oxygen being more electronegative, we move the lone pair of electrons up. Now, we have created the protonated acetone. That's the electrophile. Remember, we're always looking for electrophiles and nucleophiles. Now, notice the first reaction was acid-base. Now we're going to do electrophile, nucleophile. Our nucleophile is water. It can approach that carbon, the lone pair swings up, and again in a reversible process. It's important. Notice the arrows. Okay. Now, we have created a new oxonium ion in this case. There's the water in blue. To get to the hydrate, again, in a reversible process. Now, our acid, I simplified the mechanism in the drawing and the writing by just putting H+, but of course there is a counter ion out there. We're not worried about the detail of what that counter ion is at the moment. We'll just represent it as the conjugate base with B. We pluck off a proton, and now we get to the hydrate of this molecule. So there's the hydrate. And let me go ahead and put in the conjugate base. There's the acid. Now, notice that these steps are all reversible. So whatever other chemistry is going on in solution as we move through carbonyl chemistry, you have to remember that all of these equilibria that we're learning about are going on. Okay? Molecules are not static. They're not only vibrating, but they're always in equilibrium with whatever species are in solution. They're dynamic. Now, I've labeled the blue as well, because imagine if we reprotonated, but reprotonated the other position, the other oxygen. Okay, so this oxygen has a lone pair. If we protonate that one, again, there's an equilibrium. I want to switch colors on it there. All right, now we've created a new oxonium ion. It's degenerate with regard to the other, except that we've protonated the other oxygen. So imagine if my blue oxygen that I've put in here is oxygen 18. So we've labeled it. What will happen next, of course, is one of the lone pairs from oxygen can swing down. We'll displace the water molecule. we have a new protonated acetone. Okay, and remember that's the labeled oxygen. And now again we have our conjugate base that I've kind of conveniently left out just to make the mechanism simple. Keep it balanced as you're learning these. And this, of course, is in equilibrium with the oxygen where we have exchanged those. And in fact, this is the observable. If we put O18 labeled oxygen in solution as O18 water, we can see that shift very quickly. And that's one of our evidences for this mechanism. So that's the acid catalyzed mechanism for this reaction. We're going to squeeze in here the base catalyzed mechanism. See if I can get that in here without going off, because it's a little simpler actually. With the base catalyzed mechanism, we have hydroxide in solution already. Of course, the counterion here is, for instance, Na+, sodium, hydroxide being the base. And so with base, you get a very rapid addition to this. You create a different kind of intermediate. Since we started with hydroxide, and it's an anion. Now notice under anionic basic conditions, we make anionic basic intermediates. This is an important thing for you to remember. Under acidic conditions, we made acidic intermediates, you see, acidic intermediates, or neutral. We don't make basic intermediates under acidic conditions. And under basic conditions, we don't make acidic intermediates. We can have basic or neutral intermediates. So what's left here, of course, there's lots of water in solution. And this alkoxide can get protonated. Again, these are all reversible processes, and we have produced the hydrate. So this is acid and base catalyzed. You see I put hydroxide in right there. Let me get a different color. Hydroxide went in right here. And when I deprotonate this, remember we still have that sodium plus floating around to balance the charge. I kind of left those out to emphasize the organic portions. When we deprotonate here, we're going to again get hydroxide. So that was base catalyzed. We put hydroxide in, hydroxide comes out. The catalyst, again a caveat or rule of thumb to write down, the catalyst typically is involved in the first step. It's consumed in some way, and then it's regenerated in the last step. And we see this for the base. We also saw it in the acid catalyzed reaction. We put the acid in, and we got the acid out. I'll add here the acid back that came from the protonation, the deprotonation of the oxonium ion. Sodium plus here. So that's acid and base catalyzed. And this encompasses huge fundamentals that we want to pick up. Reversibility in these reactions, they're completely reversible. Catalyzed reactions, catalyst involved in the first step, regenerated in the last step. We go acid-base reaction, electrophile nucleophile reaction. Then what did we do? We did a base and we had an acid. Okay? We reprotonated because we're shuffling those protons around here. So again, this was a base reaction. Sorry, got that one backwards. Here's the base and the acid. And then this we can think of as an internal nucleophile leaving group reaction. And then, again, base and acid. All right. Same thing here. Bases are also nucleophiles and electrophiles. And then, so this would be characterized as a nucleophile electrophile reaction. The electrophile is the carbonyl, the nucleophile is the hydroxide. So things that are bases can also be nucleophiles.